Hello and welcome to the Basic Ultrasound course offered by the Philippine Society of Ultrasound for Surgeons. My name is Professor Ricardo Quintos, and I will be talking to you about the basic physics and fundamentals of medical ultrasound. For any ultrasound imaging system, there are major components that are found in all of these systems. So they are broken down into these major components. First is that there is pressure produced by sound that is released and picked up by the transducer, which is then brought into the central processing unit, which processes the data and the signals that are obtained by the transducer. And eventually, these signals are converted into something that can be seen, or that is light energy that can be displayed on a monitor for our analysis. So let's go through them one by one. To discuss pressure, we need to discuss what sound is. In this lecture, we will be talking about the physics of sound energy, the wave properties and their significance, and we will also be talking about ultrasound principles, the ultrasound interactions with tissue, basic ultrasound theory, and the different ultrasound modes. Sound is energy transmitted as a mechanical longitudinal wave that travels in a straight line through a medium. This is the definition of sound that will show you that all of these important components should be present for sound to occur. It is an energy that is transmitted as a mechanical longitudinal wave. It travels in a straight line and it requires a medium. Without any of these different properties, then there is no sound. So it says here that sound as an energy requires the medium through which it will travel in a longitudinal wave in a straight line for the sound to be completed. The different categories of sound are as follows. We first start with audible sound, and this is the reference point, which is the audible to humans kind of sound. And the frequencies that humans are able to hear and detect with their ears is the sound that vibrates from 20 hertz to 20,000 hertz. Below 20 hertz, it is too low for humans to hear, and that is what is categorized as infrasound. Above 20,000 hertz is ultrasound, and that also is beyond the range of human hearing. But many other animals may be able to detect infrasound, such as whales in the ocean, and ultrasound can also be detected or heard by other animals, such as bats and other insects. Now, sound, when it is produced by the vibration of objects, it will be propagated. How will it be propagated through a medium? Sound is propagated when the vibration of the source will cause a compression and rarefaction of the molecules of the medium. The compression regions are the high pressure regions or areas of increased air density, if air is the medium, or increased density of the medium molecules, and that is where we have the compression segments of the propagation of sound. The rarefaction segments are the low pressure regions or areas of decreased air or medium molecular density. So with this decreased density of the molecules of the medium, there is a rarefaction. And if you have a series of condensations and rarefactions, then you will have a wave that is then propagated throughout the medium in a particular direction. Just for academic purposes, there are two types of waves. There are longitudinal waves and transverse waves. Longitudinal waves is that the particle motion is along the direction of the wave energy propagation. For example, in segment A here, the particle motion is along the longitudinal axis, and that is along the direction of the energy propagation. The energy propagation is moved from left to right, and the particle motion is also moved from left to right. That is what is called longitudinal waves. And that is an example of how sound waves are propagated. Transverse waves, on the other hand, is that the motion of the particles is perpendicular to the direction of propagation of the wave energy. For example, here in this diagram, the particle motion goes in an up and down manner, but the waves are produced and the direction of the waves are perpendicular to the motion of the particle. These are also known as shear waves or stress waves. This is not how sound waves move. So sound waves, for our purposes, are only longitudinal waves. Now, when you talk about waves, there are certain characteristics of the waves that you will have to know, which will define the kind of wave that is being propagated. And these properties are these characteristics which describe the wavelength, the frequency, the amplitude, and the acoustic velocity. The wavelength is the distance that one complete cycle occupies. If you have a wave here, one complete cycle is a movement from the top of the wave to the bottom of the wave back to the starting point. So that is one wavelength. If you will imagine it in a static two-dimensional area, that is one cycle because it goes from up, down, and then up again. So that is one cycle. So at a particular point in the wavelength, if you start at the crest or the top of the wave, then you have to end the cycle again at the top of the wave. So that is the distance that one complete cycle occupies. Mathematically, the wavelength is a function of propagation speed and frequency. We will be talking about this later on when we talk about how waves will be traveling through certain media. The second characteristic or the second property of waves is frequency. Frequency is the number of wave cycles that pass a given point per time, and it is defined by the unit hertz. So the number of waves that pass through a given point per given time, like for example, for 1 second, that will determine the frequency of the wave. So if the waves are closely packed together, then there will be more waves per second, and that will make that wave be called a higher frequency wave. Whereas if the waves are longer in duration and there are less waves passing through a particular point at a particular time, then that will be a low frequency wave. So 1 hertz is 1 wave per second. Now, sound will usually go with many frequencies or many waves per second going through a particular point in time. And we can have 1,000 or 1,000,000 hertz going through a particular point in time, and that will be called 1 megahertz. The third property of a wave is called the amplitude. The amplitude is defined as the strength of the sound wave. The strength of the sound wave is basically the difference between the average and the maximum value of an acoustic variable. So you measure the height or the depth of the wave from the baseline, and that is the amplitude. In layman's parlance, that is the strength of the wave or the intensity of the sound, with a higher amplitude resulting in a louder sound. With a smaller amplitude, then you will have a softer sound. Finally, The acoustic velocity is one property of the wave which takes into consideration the characteristics of the medium. Because the acoustic velocity is the speed at which a wave propagates through the particular medium. And this acoustic velocity depends on the acoustic property of the media. It does not depend on the vibration of the particle. It does not depend on the element of the particle that is moving, but it is dependent on the acoustic property of the media that affects the propagation of the wave. So we note here that the acoustic velocity is not the same as the particle velocity. Particle velocity refers to the speed at which the particles vibrate back and forth across their mean positions without any mention of the media or the medium. But the acoustic velocity is the speed at which the wave moves through the medium. And there are many different characteristics of the medium that will affect the wave propagation through it. So basically, the speed of sound, which affects the wavelengths, because we did say that the wavelength is equal to the propagation divided by the frequency. And the speed of sound then is affected by the medium in which it passes. For example, for air, the characteristic velocity of sound is about 330 meters per second. For water, the speed of sound moves faster at 1,480 meters per second. Through fat tissue, it's about 1,460 meters per second. In liver, it is 1,555 meters per second. In the muscle, it's 1,600 meters per second. And note that through bone, the speed of sound quadruples to about 4,080 meters per second. To simplify, the average acoustic velocity in human tissue is about 1,540 meters per second. And this is the value which is inputted into most ultrasound machines in order to make computations as to what the average speed of sound is in human tissue. With that, we have to understand now, with using ultrasound in humans for medical purposes, we have to understand now the interactions of ultrasound with tissue. Certain concepts come into play. The acoustic interface is that which occurs whenever two tissues of different acoustic impedances or acoustic resistances are in contact. So if there are two tissues with two different acoustic properties and they come in contact, there will be an acoustic interface. Even if there is not an anatomic structure there, the ultrasound waves that will be seen, that will be reflected from this contact of two tissues of different acoustic impedances will be seen as an acoustic artifact. And we'll have to understand that these artifacts are sound artifacts and not anatomic artifacts. Acoustic impedance is basically the product of the material's density and the velocity of sound in the material. And it is also a measure of just how much the resistance of the propagation of sound is in that material medium. Here now is a table of the properties of the different media in the body and also in the environment. For air, which has a density of about 1.2 kilograms per cubic meter, the velocity of sound in air is about 330 meters per second, and the resistance or the acoustic impedance of air is very, very low at 0.0004 grams per square centimeter per second. Now, when it comes to water, which has a density 1,000 times more than air, but a velocity of 1,480 meters per second, the acoustic impedance is about 1.48. Now, looking at the tissues, soft tissue average has a density of 1,060, and velocity has an average of 1,540, which has an acoustic impedance of 1.63. Going to bone, the density of bone is about 1,912 kilograms per cubic meters, and the velocity is 4,080 meters per second. And the acoustic impedance is measured in bone. It's a very high resistance, which is about 7.8, compared to the acoustic impedance in soft tissue and compared to the acoustic impedance in bone. You will see that in soft tissue and in bone, the acoustic impedance does not differ significantly. So sometimes you will see ultrasound images of blood and the movement and the propagation speed of the ultrasound through blood and the ultrasound propagation through soft tissue is not going to matter too much. But when it reaches bone, there is a very high impedance to the movement of sound to the bone, such that it has a very high acoustic impedance. And that is why we sometimes see, or we generally see, that ultrasound will not penetrate bone and we will not be able to see the structures that are underneath the bone. So impedance is basically the resistance to sound as it travels through a medium, and it is computed by having the density of the medium multiplied by the speed of sound. Now, since acoustic velocity is dependent on the medium, we have to also understand that different characteristics of the medium will affect how sound propagates through it. Now, the properties of the medium are its elastic properties, its density, its compressibility, and its bulk modulus. The elasticity refers to the ability of an object to return to its original shape and volume after the force is no longer acting on it. The density of the object, or the density of the medium, is the mass of a medium per unit volume. The compressibility of the medium is its ability, or indicates the fractional decrease in volume or the change in volume when pressure is applied to the material. With greater compressibility, there is decreased velocity of sound. With more compressibility, there is increased velocity of sound. The bulk modulus is defined as the negative ratio of stress and strain. Stress is the force per unit area or pressure applied to an object, while strain is the fractional change in volume of the object. So pretty much bulk modulus is the ratio of the force unit or the pressure applied to the object compared to the strain, which is the compressibility of the object. An important characteristic or behavior of sound as it travels through a medium is that as the distance increases, its intensity and amplitude also decreases, and thus it becomes attenuated. So as the wave travels through the medium coming from the source, as you go further and further from the source, the intensity and the amplitude decreases and it becomes attenuated. This is an important property that we need to know, especially when we do medical ultrasound, because we have to realize that the deeper we go and the deeper we interrogate using the ultrasound, the weaker the signals become. So the deeper the wave travels in the body, the weaker it becomes. And there is a measure of an attenuation of the waveform. So if you're doing ultrasound on deeper structures of the body, you will have to realize that as the ultrasound is transmitted by the transducer, there is a certain distance that it has to travel, and there is a second distance that the echo will need to travel in order for it to be detected by the transducer. So the deeper the structure is, the weaker the echo amplitude becomes. And this is very important because we now need to adjust certain settings in the ultrasound machine in order to compensate for this attenuation and for this decrease in echo amplitude. And we will learn more about this in the following lecture on knobology, but I am introducing to you the concepts so that you will know that this particular property and behavior of sound through tissue is an ever-present phenomenon that needs to be compensated for. Now, what causes these attenuations? Attenuations can happen because of reflection and scattering as the sound waves hit the different media or the different molecules of the medium. There's going to be reflections and scattering, and it's not going to travel really in a straight line, but it's going to hit molecules and travel to another direction, which makes it lose energy, and this loss of energy will result in a decrease in amplitude. So that is one of the attenuation mechanisms, but this is a minor effect because most of the attenuation mechanisms occur because of absorption effects. And absorption effects, being a major attenuation mechanism, is also affected by the kind of frequency. Absorption is frequency dependent. Higher frequency sound will tend to be absorbed quicker than lower frequency sound. So that means that lower frequency sound can travel much further than higher frequency sound because the attenuation is much lower with lower frequencies than with higher frequencies. Therefore, where penetration is needed, low frequency probes are usually required. And we will talk about these transducers later on when we go into transducer theory. So attenuation, or the decrease in ultrasound amplitude, increases with frequency. Now we now know that sound used for medical diagnostics is above 1 megahertz. And sound above 1 megahertz cannot, due to reflections, enter air. So again, for tissue reflections or tissue interactions, if there is air within the tissue, the sound, being a higher frequency, is already being attenuated by the distance. And then as it enters an air gap, it cannot be transmitted further on after the air gap because the attenuation happens here in this air gap largely because of reflections and absorptions. So that is why in ultrasound, it is very important that we try to insulate the areas of the body which have less gas. And if there is gas in that area, we have to prepare the patient to remove the gas from that area. So that is why if you're going to do abdominal ultrasound, we don't want to have the patient fed a few hours before the procedure, because in feeding, the patient will be swallowing a lot of air, and a lot of air is going to be seen in the intestines and this intestinal air is going to block the transmission of sound because of this air gap. To repeat, the attenuation results from absorption or the conversion of sound energy into another form of energy, which is usually heat. So higher frequencies undergo greater absorption. Now, this is important later on when we talk about the ultrasound safety, because although we know, and although it is generally known that ultrasound is generally safe, we know that the absorption mechanism of attenuation will convert mechanical energy or the vibrations into heat energy, and that results in the attenuation. So ultrasound produces heat energy. And this phenomenon is actually being used by certain devices for sterilization of instruments. Instruments can be sterilized using ultrasound because the heat energy that is produced can be harmful to the bacteria. And so it is also important for us to know that prolonged insonation of a certain location in the body may result in a temperature increase of that particular location if you keep the probe there long enough. So we will be talking later on in another module about ultrasound safety, and you will be introduced to the principle of ALARA, which is as low as reasonably allowed. And that is the basic principle of ultrasound safety, where we should only use ultrasound for its intended purpose and not for anything else, because it is a form of energy that can and does have certain harmful effects if not watched out for. Okay, now the minor forms of attenuation are reflection and scattering, and sound is reflected when it reaches a boundary between two dissimilar media, and this is what we call the acoustic interface. So if you have blood and fat, or fat and muscle, this boundary between them, you will have an acoustic interface, and you will have this reflection that we will be able to see in the ultrasound machine. Now, scattering occurs when an ultrasound wave strikes boundaries between two media that have irregularities, and the wave is scattered in different directions. Therefore, the echo of the wave that hits that particle bounces up in another direction, and it is not reflected back to the transducer. And so the transducer will detect it as a weaker signal compared to how it was transmitted. Now, since attenuation is a predictable mechanism, it is compensated for by a time gain compensation. And fine-tuning of this gain compensation is typically done using a number of slide switches or slide potentiometers. And because of that, with this predictable decrease in signals along the depth or along the distance traveled by that sound, we can adjust the time gain compensation to increase the sensitivity of the probe to the smaller amplitude waves, such that we will have a pretty much uniform homogeneous wave that is detected by the transducer and then worked on by the CPU. And so if you do not have this time gain compensation, you will see that closest to the probe, it's very, very clear, it's very, very visible, but farthest from the probe, it's going to be very dark, and maybe the resolution is not going to be very good. But with the time gain compensation, you can adjust certain switches and certain knobs in the ultrasound so that the weaker signals will be strengthened, will be picked up more, and the signals will then become equal to the signals obtained uh, from the echoes come closer to the ultrasound probe. And then you will have a more homogeneous image. So more of this in the lecture on knobology following this module. So we talked about the pressure, and now we will be talking about the transducer, which job is to produce the ultrasound so that it will be transmitted to the organ of interest. And then it also picks up the echoes of the sound so that it will then be analyzed by the CPU. The analysis of the CPU will then move the data to the monitor for visualization. So basic transducer theory is that the transducer produces a beam which is directs the acoustic energy produced by a transducer. This beam is produced by a transducer. This transducer is a device capable of converting energy from one form to the other. In this case, electrical energy to mechanical energy, and vice versa. In ultrasound, the term transducer is used to refer to the crystal and the surrounding housing. There is a housing or a probe, if you will, that houses a crystal, a live electrode crystal element that works by vibrating, and this crystal that vibrates is the one that produces the particle vibrations to make ultrasound. So there are different kinds of transducers. There are mechanical transducers and there are electronic transducers. At this present day and age, we rarely see now mechanical transducers. This was the first generation ultrasound probes. Now we will almost always see electronic transducers with the elements arranged in an array, and there are multi-element electronic transducers that allow it to operate at different frequencies. So this is the mechanical transducer. You will see here that it emits a wave, and the mechanical movement of the array allows it to sweep back and forth so that there will be a accumulation or a collection of ultrasound reflections, which is then collected by the central processing unit and analyzed and brought out to the display monitor. But the electronic array transducer actually has multiple beams being transmitted out. So it's not a mechanical event now transmitting beams at the different angles, but we now have multiple beams coming out from the array. There is an array of crystals that will allow the beam to be propagated or to be transmitted away from the transducer. And there are different types of array transducers. You will have here a linear array, which means that the beams are transmitted longitudinally in a flat manner such that the footprint of the ultrasound transducer or probe is nearly the same as the beam being transmitted. The curvilinear array has a convex surface that allows a diffusion outwards of the beam such that the beam and the image that can be picked up is much greater than the footprint of the transducer. So how does this crystal produce sound? That is explained by the principle of piezoelectricity. Piezoelectric crystals are the primary components of an ultrasound transducer, and they're made of lead zirconate titanate material, and they convert electrical energy into acoustic energy during transmission, and vice versa. Acoustic energy into electrical during reception. So if this is a crystal and you have electrons traveling through it, if the electrical voltage is supplied and you have electrons traveling through this crystal will then start to vibrate. So there is a conversion of electrical energy into mechanical energy. This vibration at a particular frequency will create the areas of compression and rarefaction and thus result in ultrasound propagation. It also works the other way. If sound waves hit the crystal and these propagated sound waves of compression and rarefaction makes this crystal vibrate, the vibration of the crystals will induce movement of electrons, and thus mechanical energy is converted into electrical energy, which is then interpreted by the CPU. And then there's another conversion of electrical energy into light energy so that it can then be seen now onto display monitors. So the piezoelectric effect is the effect caused by crystals changing shape when in an electrical field or when mechanically stressed, so that an electrical impulse can generate a sound wave or a sound wave can generate an electrical impulse. Now, there are different modes of transducer operation used in medical ultrasound. The first mode is the continuous mode or the continuous wave transducer. With this, there is one crystal that vibrates and a separate crystal element that listens for the returning echoes. So there are separate elements for the transmission and the reception of ultrasound. For pulse transducers, the same element crystal is the one used for sending and receiving the sound energy. So what will happen is that the crystals will vibrate for a certain period of time, and then it will stop and listen for the echoes. And when the echoes arrive, the echoes make it vibrate, and then the vibration will create electrical energy that will be sent back to the CPU. So the pulse transducers will pulse and then listen, will transmit and then listen. And so it is up to us to apply the settings of the pulse on how long a period of time that they will pulse and how long a period of time that they will listen for the echoes. And again, in the lecture on knobology, you will be told how this is very important in adjusting now for the improvement of the detection of the ultrasound. So this is a figure example of a continuous wave mode where there are two different piezoelectric elements. One element will continuously vibrate and send forth the ultrasound signals. And this will be echoed back and picked up by a second transducer or a second crystal, which then transmits or converts the mechanical energy into electrical energy, and electrical energy is brought into the receiver, and this receiver is then interpreted by the central processing unit, and then it's again amplified and brought out to a speaker, so you are able to hear the sound. If it is not through a speaker, it is brought out through a display monitor where sound is converted into light energy. Now, the pulse wave system, you only have one crystal which vibrates for a certain period of time, then it waits for the echo. And it is this system that sends forth the signal and receives the signal and sends it back to the central processing unit, where it can be shown as a monitor display, or it can be uh, demonstrated and amplified into a loudspeaker. So we've been talking about echoes being picked up by the transducer, and this is now an important concept, the concept of pulsed echo principle. When an electrical pulse strikes the piezoelectric crystals and produces a wave that propagates through the tissue, then the echo is picked up by the crystal, and then it generates an electrical signal that is sent to the central processing unit. The returning waves are converted into electrical impulses that form the ultrasound image. So again, the beam is the directed acoustic field produced by a transducer, and the transducer is the device that is capable of converting energy from one form to another. We have to look now at the beam anatomy, because the beam anatomy and the beam behavior can affect how the transmission of sound and how this sound can be processed further. Now, because of the pulse echo principle, we want to capture as much as possible, as many echoes as we can, because if we do not capture too many echoes, then the energy is lost or the sound is lost through scatter, and you will have a very weak amplitude. So you want to orient your ultrasound probe into, as much as possible, a perpendicular location to your organ of interest. So if this is the surface of your organ of interest, you want to position your probe such that the beam is nearly perpendicular to the surface of the organ of interest, so that you will have strong echoes coming back. Because if they are not parallel, or if they are not perpendicular to the direction of the waveform transmitted and reflected, then you will have a lot of scatter, and you will only be able to capture very weak signals. And there is going to be a great degree of attenuation in your reception of the reflections and echoes. Looking at the beam and the beam anatomy, we know that it is a longitudinal beam, but the beam has a focal point. The beam has a focal point. And there are two areas or two regions in the beam: the region before the focal point and the region after the focal point. This is very important to know, because the organ of interest, wherever it is in the beam anatomy, it may result in very poor resolution. So resolution is just defined as the ability of the system to discriminate or to differentiate adjacent points or adjacent structures. So if you have good resolution, then that means you are able to resolve two different points or two different structures. Because if you cannot resolve them and the two structures are seen as one, then there is very poor resolution, and then you get a very blurry image. Beam anatomy has a lot to do with resolution. As much as possible, you would like to have the organ of interest at the focal point of the beam, and you will have to adjust your machine to put the focal point to your organ of interest. However, if your organ of interest is at the region that is closer to the transducer, or what is called the near zone, this near zone can also afford good resolution. So there are two kinds of resolution. Axial resolution is the ability to distinguish between structures along the path of the ultrasound beam. So if this is your focal point over here, and these are your organs or target organs of interest, at the focal point, you will see that the target structure is well resolved. And at the focal point, these two structures can be seen as two different structures, so they are well resolved. But in the far zone, you have two structures here, but it will come out in the ultrasound as only one structure. Then these two structures are not finely resolved, and you only see one structure, which is a very bad a resolution. So you will have to position the structure into your focal point or closer to your focal point in your near zone in order to have a good resolution axially. The same thing happens with lateral resolution. Lateral resolution is the ability to distinguish between reflecting surfaces perpendicular to the path of the ultrasound beam. So in this example here, you have 3 points, and there is, because it is in the far zone, the resolution is so poor that point 1 and point 2 is not completely resolved, and it can be seen only as one structure. Now we can resolve point 2 and point 3 as different structures, but point 1 and point 2 are not resolved, and so there's poor resolution at this level. So this is where we now understand why we need to put structures of interest or organs of interest at the focal zone, or at least closer to the near zone. Or this near zone, or what we call the Fresnel zone, is the area between the transducer and the focal zone. The focal zone is where the diameter of the sound beam is at a minimum, and that is where there is a very, very clear resolution. And the far zone is the area extending beyond the focus. This far zone, or the Fraunhofer zone, will offer you only very, very low resolution. See, in here in the Fresnel zone or the near zone, you can still have very good resolution, but after the focal point, you will not be able to resolve the two dots or the 3 dots, and you will just see them as singularities. Now, what can affect the focal point? And so what can we do to improve the focal point of the ultrasound beam? The length of the Fresnel zone or the length of the near zone can be affected by the size of the transducer. And it can also be affected by the frequency of the vibration. If you have a lower frequency, then you will have only a shorter near zone. Okay? If you have a higher frequency, then you will have a longer near zone. So here, with the same size of the transducer being kept constant, but the frequency is increased from 1 megahertz to 3 megahertz, you will see that the near zone is becoming more elongated. And so you will be able to see a little more good resolution with higher frequencies as long as it is kept in the near zone. So the second variable is the size of the transducer. The near zone is elongated if the transducer is increased in size. So here in this diagram, with a frequency being kept constant at 1 megahertz, with the size of the transducer becoming bigger and bigger, you will see that the length of the near zone is becoming longer and longer. So that with the size of the transducer, you're going to have a longer near zone, which means you will have a greater distance of a higher resolution. So talking about frequencies, again, I bring this back. Higher frequencies will have a high resolution, but the caveat is that it will also have a high attenuation and therefore low penetration. Lower frequencies will have low resolution, but there is low attenuation, so it can travel further. It can travel longer distances, and thus it has a higher penetration into our bodies. And so when you choose a probe, when you're going to buy your ultrasound, you will need to know what usual target organs you're going to use or you're going to detect, because that is the frequency of the probe or the transducer that you will need. If you're only going to look at superficial structures, like structures at the skin, subcutaneous area, or even up to the muscular layer of the extremities, of the soft tissues of the neck and of the breast, then you will need a higher frequency ultrasound probe. But if you are going to look at body cavities or body depths, like the pelvis, the abdomen, the heart, which is situated kind of deep inside the thorax, then you will need ultrasound frequencies of the lower frequency kind, because they will have low attenuation and high penetration. But remember, they will also have low resolution. So applications is that the transducer frequency you will choose to buy or you will choose to procure, if you're going to use it for abdominal, trauma, cardiac, obstetrics, you will want to get transducer frequencies from the 2.5 to 5 megahertz range. If you're going to use it for pediatrics, prostate, rectal, transvaginal, intraoperative ultrasound, you usually use a higher transducer frequency of 4 to 8 megahertz. Now, if you're going to look at small parts, the breast, testicular parts, vascular, muscular, endorectal, you want to look at the different layers of the anorectal region, then you need a higher frequency because it is very shallow. You don't need one that penetrates very, very deep, and it affords a very, very good resolution at that frequency. So here is just a diagram of the pulse bandwidth and resolution. The resolution is affected by the pulse bandwidth. We talked about the pulse echo principle, and we talked about pulse wave versus continuous wave. So the pulse wave will have an effect on your resolution. So if you have a longer pulse, that means you will have a narrow frequency, then you might be able to get a greater resolution with a longer pulse. But with a short pulse, you have a broad signal there, and you have only one frequency. Then again, you have a low frequency. Then you have a very low resolution in that situation. So you will have to learn in your knobology how to adjust your pulse frequencies. The transducers in the older days are designed with only one frequency per transducer, and that is why you have to specify to your ultrasound distributor what kind of transducer and what kind of frequency that you would like to use for your particular uh, use. Currently, though, transducers are designed with a high bandwidth and can be operated at different frequencies. The user is able to control the trade-off between penetration and resolution for the same transducer. So now all you need to do is tell your distributor, I want these frequencies and I want them included in one transducer. So now there are now settings in the ultrasound machine where you can change the frequency. Before, you used to buy a different probe for a different frequency. Now there is such a concept as multi-frequency imaging where you can change the frequency settings of one transducer. So finally, we come now to the final component, which is the conversion of the electrical energy into light energy so that we can now see what the ultrasound echoes have been picked up. So there are a few different kinds of imaging modes. You have your amplitude mode, you have your brightness mode, you have your color flow mode, you have your Doppler mode, and you have your M motion mode. And then any combinations of the above will lead to the terminology of either a duplex or a triplex ultrasound. A duplex mode will mean that there's either a brightness mode or a B mode and a color flow mode brought together in one screen. So if you can have that, both modes active in one screen, then you have a duplex ultrasound machine. But if you have a B mode and a color flow mode and a Doppler mode all together working in the display mode, then you have a triplex mode machine. And this requires a lot of computing power for the ultrasound to be able to display this into the monitor. So the A mode imaging system is the simplest. Basically, you have here a transmission of the impulse, and then you have the reflection of the impulse of the different structures. And so the intensity of the echoes are just displayed as intensity of light. So you will see here that the intensities of the lights are seen at different distances because there is a structure. For example, the structure of the skin, and then the organ of interest, and then the spine, and then there's the in-between retroperitoneal tissue. And then you will see these these amplitudes, which will tell us that the echoes here are bright, the echo here is not so bright, the echo here is not so bright, and this one, the echo here, is a bit bright coming from the bone. And these are the waveforms that were picked up by the echoes. And you will see this bright lights in the ultrasound echo monitor. The main benefit of this is that you can measure the distances of these amplitude signals so that you will know what their relative distances are to each other. The B mode imaging system is the brightness mode, is basically a series of A modes brought together. Now, there is a sweep of the different A modes brought together, and then you will see a two-dimensional grayscale of the reflections of the structures of that pass through the ultrasound beam. So with that, you will see that there are higher intensity echoes, lower intensity echoes, no echoes, and putting them all together, you will be able to see what is called the grayscale. So this is the grayscale of the B mode, and the grayscale can have as much as 256 grayscales, points of intensities or even higher, 512 or even higher. The cheaper ones will only have about 128 grayscales, which will not give you too much good resolution. But in general, having 256 to 512 is okay, different shades of gray. All right. Now, the M mode is again also a combination of the A mode and the B mode, except there is now the element or the dimension of time. When there is a movement, during movement, so when this organ is moving and the echoes are being transmitted at the relative changes in position of this moving echo, then if you run that across the dimension of time, you will see here the movement of the organ of interest elongated across a time dimension. So this is pretty much used in many self-moving organs. For example, the heart, as the heart is beating, you're able to see the movement of the valves, the movement of the ventricles and the atria, and you will see them plotted against a longitudinal axis of time. And looking at the waveforms, you will see whether the valves are closing properly or moving adequately, or if the contraction of the ventricles are adequate or not according to the norms set by thousands of previous studies. Now, before we go to the color flow mode or the Doppler mode, we need to know what is the Doppler effect. The Doppler effect is what we usually hear when there is movement, and for example, the source of the sound is emanating from this moving object. Since sound travels, or the speed of sound is constant, if the object is moving with the source of the sound, the velocity of sound is not additive to the velocity of the source. So if the source is moving, then it will tend to compress the sound waves ahead of it because of its velocity. So if there is a compression of the sound waves in front of the moving object, then you will see that the frequency of the sound in front of the object is higher than the frequency of the sound at the rear of the object. And this changes the pitch of the sound. So you will hear that the sound, as it comes to you, as the object is approaching you, the frequency is higher, so the pitch is higher. And then as it passes you, the sound pitch becomes lower. Such like it goes like, it's like a whoosh. No? When you watch racing cars or the train or an ambulance going, passing you, you will hear the siren going at a higher pitch and then becoming lower as it passes you. That is called the Doppler effect. It also happens if the source of the sound is stationary and there is an object that is going towards the transmission of sound. And when they meet and the echo is transmitted back to the transducer, then that will have a higher frequency compared to the echoes at the back of that particle. So that is the principle of the Doppler effect in ultrasound. If you have a stationary transducer, the velocity of the sound as it is transmitted will be the same velocity as it is reflected. If you have a structure, for example, a red blood cell that is moving towards the transmitter emitted a certain frequency and then will receive the echo that is of a higher frequency because it is moving towards the transducer. If this red blood cell, for example, is moving away from the transducer, then the velocity as it is transmitted and hits the moving object that is moving away from the transducer, the reflection is going to be a slower or a lower frequency. So that is the Doppler effect. And for Doppler geometry, of course, for maximum Doppler effect, you need to have the beam really parallel to the direction of the flow. But it is kind of impossible to put a ultrasonic transducer at the end of a blood vessel like this, end to end, in order to get the ideal Doppler angle. So suffice it to say that the most acceptable Doppler angle that is by convention agreed upon is to hit the moving particles at 60 degrees angle. And this is the agreed upon angle for the Doppler geometry, for that the computer can compute and make extrapolations or interpolations as to the actual velocity of the moving red blood cells or the moving particles using this Doppler equation. We will not go into this into detail, just understand that there is such a Doppler equation that is fitted into the CPU so that the machine will be able to interpret and extrapolate the actual velocities using the equation. Okay, this slide just shows you that the Doppler angle dependence. So ideally, we want this angle at a parallel to the direction of flow. But since we cannot do that, we want it at 60 degrees as a maximum acceptable. Any more than that, going at 90 degrees, that's unacceptable because you will not be able to really see accurately the velocity as the red blood cells move away from or towards the transducer. So this is, again, the ultrasound system. Transducer, transmitter, receiver, detection, beam mode, scan conversion to the monitor. And this different frequencies by the different Fouriers or the different Dopplers are picked up and plotted along the waveform. And using the principle of fast Fourier transform, we now come up with a waveform that is actually a demonstration of the different frequencies and the velocities detected by the transducer. So the highest frequencies or the highest velocities will be at the top of the waveform, and the lowest frequencies will be at the baseline at 0. And then if you have particles moving away from then the transducer, then you will have a negative deflection in the waveform. And so there, with that, we now come to the discussion on color flow mode. Color flow mode depends on Doppler because it will tell you, it shows in the monitor qualitatively with the intensity, or semi-quantitatively with the intensity of the color, the velocity of the movement of the particle, and thereby the frequency of the vibrations. So when you have this color flow mode, it's not actually because of the color of the content, of the organ being examined, but it's really more of the color arbitrarily set by ultrasound manufacturers for certain frequencies and certain velocities. The blue, it can be set as a direction of a movement away from the transducer, and the red can be set as the movement going towards the transducer. So by a convention, if you have an arterial flow, they just set the direction of flow so that the Doppler color is set to red, and the color direction is set to blue for the veins, because we do know that their directions are generally opposite to each other. So that is what is called color flow scanning. Now, power Doppler does not take into consideration the direction of the flow, but only the intensity or the speed of the particles, and also the rate or the frequency rate of the particles. So the higher the frequency, the more intense the color, but there's only one color. It will not tell you the direction of the flow. Okay, now this image now shows us what is called the triplex using the power mode. Triplex because there is a B mode or the grayscale mode. There is a power flow mode. Remember, there's only just one color because of the power flow mode, but it gives us the intensity or the velocity of flow. And you have here at the bottom the Doppler frequency spectrum. Now, it is said here that this is the velocity, but this is pretty much the highest frequency, and this is the lowest frequency, and this is the negative frequency, which says that these are the particles or the frequencies that are moving away from the transducer. So this is now the triplex mode. Now be wary when your ultrasound company will try to sell you a machine that she will claim to have, or he or she will claim to have triplex mode, and will show you this image. Some machines are not really duplex modes or triplex modes, but they will have this kind of image. Why? Because the B mode is actually just a frozen image. The power mode is also just a frozen image. And the only image that is moving is the spectral Doppler, the Doppler mode. So that is not even a duplex. That is just a single mode display, because only one mode is active. For triplex to occur, you have to have an active real-time movement of your Doppler. You have to have an active real-time movement of your B mode, and you have to have an actual real-time movement of your power flow mode. And that requires a lot of computing power, and that's why triplex machines come at a very expensive price. If you have a triplex with a color flow mode, then you will have a machine that will give you the bidirectional indicator, no, of a red and a blue. And you will still also have the grayscale, and you will also still have the frequency mode spectrum, all moving in real time at the same time as your triplex machine. And finally, you will have here what is called the 3D and 4D ultrasound, which is really not just a duplex, but these are really a more computing power applied to two-dimensional images, that you create a sweep and it creates a 3D image. If the 3D image is static, then that is just a 3D ultrasound. So here you have a 2D ultrasound, and now you have these 3D static images. But if you add here now movement to the 3D, then you will have a 4D ultrasound. Now, if you rotate the 3D, that is still not 4D, because this is frozen in time. This is just still a still picture, frozen in time. But the 4D ultrasound is one that shows you actual movements in a 3D environment. So here is the 4D ultrasound, and you are actually seeing movement in 4 dimensions, and you can get machines with very, very strong computing power that can display the ultrasound images in 4D. Okay, to summarize, for the fundamentals of ultrasound and the ultrasound physics, we talked about pressure, the physics of sound, how sound behaves, the characteristics of sound, the properties of sound, the properties of media that affect its acoustic characteristics. And then we talked about the transducer, which transmits and receives the sound. And we talked about the beam anatomy and the beam theory. And then we talked about how the beam is then computed by using certain assumptions on the acoustic velocity and the length of and the depth, and how to adjust the images so that you will get better resolution, so you will get better signals, how to use your probe so that the processing unit will be able to have a better processing of the data that came in. And finally, we looked at how this data is then displayed either through loudspeakers or through the monitor using the different modes of A mode, B mode, C mode, D mode, and M mode. Well, with that, we end this lecture on the basic physics and basic fundamentals of ultrasound. And I applaud you for joining this course, because we now know that ultrasound is really an essential aspect in our surgical practices. And doing this, we can now do ultrasound as a point of care in the field anywhere we do our procedures, in the emergency department, in the operating room, even in our clinics, and of course in our laboratories. And ultrasound has become such an essential tool, such that it is now being used in the field, in the military, and in the waypoints of Mount Everest, in extreme environments, up to even the space shuttle in the maintenance of health of the astronauts living there for extended periods of time. So with that, I would like to thank the organizers for inviting me to give this lecture to you. And I again congratulate you for taking the first step in learning how to use ultrasounds in your clinical practice. Thank you, and stay safe.